Okay, so today's talk is from one of the projects IRIS-HEP is contributing to. This is the sort of a MK-FIT project, which Allison will talk much more about. But just the one sentence introduction is looking at how to speed up common filtering algorithms, and they're looking at this in the context of CMS. But I think much of what they'll end up with product-wise is something that anyone will be able to use. So, with that,
David,
yeah.
David, the recorder.
I'm not. I am recording. Yeah, so I am recording. Which is okay for you?
Yes, that's fine.
Okay, we try to put these things on YouTube afterwards to keep track of them.
Okay, yeah, that's fine.
Okay, now you could really go ahead.
Okay, so as David mentioned, I'm presenting on behalf of the MK-FIT group, which is a collaboration between Fermilab, Cornell, Princeton, UCSD, and Oregon. So the names are listed here, and you can see the two websites for the project listed above, and I'll describe why we have two in a little bit. Okay, so first of all, to explain what's the problem that we're trying to solve. So the picture you see here is a real event taken with CMS in a high pileup run in 2018. And so here we have a pileup of 136, which means we have 136 overlapping proton-proton collisions to deal with in this event. And so how we distinguish all of this and make sense of this is through tracking. And tracking really is crucial for collider physics experiments. We use it to estimate the charged particle momentum. We use it in particle flow algorithms. It's essential for MET, it's essential for B-tagging, and so on. So there's a lot that requires tracking to work well. But in addition to being crucial, tracking is also time-consuming. So over 50% of the time it takes to reconstruct one event in CMS is spent doing tracking. And the problem is that time is only going to go up. So the problem is only getting worse as more and more of our events start to look like the one you see at the bottom. And so as we get to higher luminosity, we really need to find new ways to deal with this tracking problem. And so that's going to be especially important for the HLLHC. So right now, we just finished run 2, and so we're in the long shutdown 2. But by the time we get to the HLLHC, the instantaneous luminosity, so the x-axis on this plot on the right, will be 5 to 7 times 10 to the 34, and the average pileup is going to be 200. So this plot shows the time it takes to reconstruct one event as a function of instantaneous luminosity or pileup. So pileup 200 isn't even on this plot. And the two lines show how much time it takes for the full CMS reconstruction versus how much of that time is spent in tracking. So you can see that the time it takes to reconstruct one event is going up like crazy with pileup, and tracking is a large contributor to that. So again, like I said, we really need to investigate new solutions for tracking. And in particular, we want to be doing that now so that we can test it in run 3, which starts in 2021, and then be ready to go and have a working solution by the time the HLLHC starts in 2026. So in order to solve this problem, we sort of took motivation and inspiration from this plot on the bottom right. So this shows the microprocessor trends for the last 40 years. And there are a couple important things to note from this plot. So the first line to look at is the one in green, so the frequency or the clock speed of CPUs. And that hasn't been rapidly increasing for a long time. So that's been pretty flat over the last couple of decades. So we can't just expect new CPUs to have higher clock speeds. This corresponds to the change you see in the single-thread performance in blue, where most of the gains in single-thread performance are now no longer from increasing clock speed, but instead are from vector operations, or SIMD, so single instruction multiple data operations. And then the other thing to note in this plot is in black. So the black line shows the number of logical cores, and that has been starting to skyrocket in the last 10 years. And so in order to take advantage of modern CPUs, we need to rewrite our algorithms to take advantage of both the parallelization, so the increase you see in the black line, and the vectorization, so the blue line that is still increasing a little bit. And right now, our algorithms are not optimized to take advantage of either of these. And so that's where our project comes in. So we're the Parallelized Common Filter Project, or the MK-FIT group, where MK-FIT stands for the Matriplex Common Finder or Fitter. And this project has been going on for the last 3 years or so. And we're trying to adapt traditional common filter tracking algorithms in order to maximize the usage of vector units and multi-core architecture. So to take advantage of both of those trends that we saw on one of the previous slides. We're writing our code, as David mentioned at the beginning, in order to just use the traditional common filter tracking algorithm, but our first goal is to be useful in the CMS HLT, where we plan to test the algorithm online in run 3 so that we're fully ready to deploy it in the HLLHC. Right now, we're testing the algorithm on Intel Xeon and Intel Xeon Phi machines, but longer term, we do plan to adapt the algorithm to run on GPUs, but that's not going to be covered today. And our focus is only on the track building, so not on the track seeding or the track fitting. So I'm actually not funded through IRIS-HEP. I'm funded through a SciDAC project. So I'm at Fermilab, and Fermilab and the University of Oregon are collaborating on MK-FIT as part of a 3-year SciDAC project. And so this is sort of just a little plug for our project. So ours has a little more of a broader scope in that we're looking both at track reconstruction in collider experiments and reconstruction for neutrino experiments. So specifically those neutrino experiments using liquid argon time projection chambers. And the approach is very similar between the two applications. So in both cases, we're trying to write faster code that takes advantage of parallel architectures, and then eventually incorporate the algorithms back into the software frameworks of the experiments so they can actually be used and benefit the experiments. Okay, so I thought it'd be useful before I dive into the details of our code and how we do it to spend a little bit of time talking about the common filter and why we use it and how it works. So the common filter has been the algorithm of choice for track finding and fitting in high energy physics for a while. And that's because it has demonstrated physics performance. So in particular, it's really good at handling multiple scattering, energy loss, and other material effects very robustly. And we have a pretty large material budget in these experiments in the trackers, and so we need to be able to handle these material effects well. The common filter is a 2-step process. So you start with the track state on layer n-1, and that's the blue dot at the bottom. And you want to figure out what the track state is on layer n. So the first step is to propagate your track, or your state, to layer n. And so then you get the state in gold. Once you're there, you can look for compatible hits, as shown in red. And then the actual Kalman update is combining those two to get your new track state measurement. And then this is an iterative process, and then you can continue on the remaining layers. And so that's kind of summarized here for how you would build all of these up into a track. And here, the point of this slide is to highlight the fact that the common filter is not straightforward to vectorize or parallelize. And the reason for this is sort of what's shown on the right. So if you start with the seed track at the bottom and you build up your track, you can either have one hit per layer if you're really lucky, or more likely you're going to have missing holes or missing layers, or you're going to have to branch out. And in vectorization, branching makes things difficult because then you can't be doing the same operations in lockstep. Similarly, because the number of possible track candidates can be different per seed, and the number of hits can be different per track, and the number of tracks is different per event, it's also difficult to figure out how to parallelize this well, because you want to make sure that each task finishes at around the same time. So dividing up the tasks is also a big part of doing this well from our point of view. So this is how we handle it. So for parallelization, we use the TBB library from Intel. And the main reason for that is that's what is used in the CMS software, so CMS SW. And we parallelize at 3 different levels. So we have a parallel for loop for n events in flight that we can process at the same time. And then within each event, we parallelize over 5 regions in Ada. So we have the 2 end cap regions, the 2 transition regions, and then the barrel. And then within each region, we're going to process 16 or 32 seeds per batch. And finally, then once we get down to the vectorization level, so once we have individual track candidates, then we also want to do vector operations as much as possible. So for the propagation, we rely on compiler vectorization. But for all of the common update and all of the common operations, we rely on the matriplex library. And so that is what is described on slide 11. So the matriplex library is sort of the core of our algorithm. And it's a custom-built library for the vectorization of small matrix operations. We looked at what existed out there, pre-existing libraries that we could use, but didn't find any that did what we needed to for small matrices. So at most, we're dealing with 6x6 matrices in tracking. And so how the matriplex works is that we use a matrix major representation. And so you've got the vector unit on the left that you want to fill with elements of your matrix. And so we actually fill it with the same element from the 8 or 16 different matrices. And then we're going to operate on all 8 or 16 of those matrices in sync. Another key feature about the matriplex library is that it includes a code generator. In order to generate the C++ or intrinsics, you need to do matrix multiplication for a given dimension. And particularly important is that you can tell it about zeros and ones in your matrices to reduce the number of operations and to reduce the memory access by up to 40%, because then you just don't have to bother touching those operations at all. And as I mentioned, this is what we use for all of our Kalman-Filter operations in the algorithm. So far, all of that has been a pretty general solution, but as I mentioned, our primary goal is to be useful in CMS, in the high-level trigger, so the software trigger for the HLLHC. And so I'd like to spend a little bit of time talking about how we've integrated our algorithm into CMS. So there's 2 different ways that we can run our code. The first is standalone, where the input is just a simple memory dump of all of the data structures, so the hits, the seeds, and then the reference tracks that we'll need. And this has really been useful for development and for the validation of our computing performance. So I'll show results today from the standalone code. But we also have a version of the code that has been integrated into the CMS software, into CMS SW, and that was really a crucial goal for us. So MKFit is still an external package, but it's compiled separately, but it can be completely used in the flow of CMS SW. Here, rather than relying on this memory dump, we have to pull the data from the CMS SW data structures, format them into our data structures, and then after building, format them back into CMS SW track candidates the way it expects. And we're trying to test this in 2 different configurations. So we're testing against the offline reconstruction of CMS SW, and that's mostly the results I'll show today. And then we've also started to compare it to the online, to the HLT software trigger version of CMS SW, and that's a work in progress, and we hope to show results for that soon. And so a key point from this that will come up again later is that, especially in the version that's integrated into the offline CMS SW, we've learned recently, or we've learned the hard way, that data structure conversions are costly. And so this going from CMS SW to MKFit and back takes a lot of time, as we'll show. And so one of the key pieces moving forward is to find ways to mitigate this between algorithms and to restructure or settle on new data structures that actually make sense to carry around for algorithms like this that are optimized for parallel architectures. Oops. So an important part of CMS tracking is that it performs the tracking over several iterations. So in each iteration, you're starting to find more and more difficult tracks. And so this plot shows the efficiency, so how many tracks are built in each iteration as a function of the vertex radius. And so in MKFit, we're focusing only on the initial iteration so far, although it would be easy to extend and optimize for the other iterations as well. So today I'll just be comparing MKFit directly against the first iteration of CMS SW, where we're trying to find the easiest tracks, essentially, so tracks that have 4 hits in the seed and no beam spot constraint. Okay, so first a little bit about the CMS tracker. So this is an example of the CMS End Cap Disk. And so CMS has 2 parts to its tracker. So there's the silicon pixels closest to the beam pipe, and then silicon strips. And the pixel region closest to the beam pipe is used for seeding. So this is what the end cap disk looks like in person. So this is in real life. This is all the detail and complexity that goes into a CMS end cap disk. One of the features of our algorithm is that we chose not to deal with this full complexity. And so that end cap disk in our algorithm is one of these lines on the right. So on the right is the full geometry that is needed for MKFit. So you just need the layer centroids and then the layer size. And so this confusing end cap disk with all of the modules and overlapping layers has just been reduced to that one rectangle. And this is a choice in order to make our algorithm faster and more lightweight, in order to help gain get some of the speed up that we see. One of the consequences is that we will plan to use the current final fit that's done in CMS SW in order to get the final track parameters, so that we don't lose on precision and resolution by ignoring all the geometry. So this is just for our building. Another key point about the geometry is that it's implemented as a plugin. So the core algorithm is entirely separate from the detector geometry. You just need a plugin, what's shown on the right, and then the layer plan of how you would traverse those layers in order to look for hits. So right now we're testing on the CMS 2017 geometry. Earlier we were testing on our sort of cylindrical cow geometry, but all you need is to develop the plugin in order to swap in a different detector or the CMS LHC detector geometry. So what we do is we propagate the tracks to the center of the layer and then look for hits in that layer. And another feature that is different than the current CMS SW tracking is that in overlap regions, we only pick up 1 hit. So we pick up the single best hit and then move on. Okay, so I've explained a lot about some of the details of how our algorithm works, so let's actually look at some results. So here I'm showing the algorithm level efficiency versus PT on the left and versus ADA on the right. So CMS SW is shown in black and MKFit is shown in red. And this is in simulation on a TT bar pileup 70 sample. And so there's a couple things to note here. So first of all, this is just the algorithm level efficiency, so we're not including like the seeding efficiency or anything like that, just the portion that's supposed to be done by our algorithm. One other thing we'd like to point out is that we're at least as efficient as CMS SW across the full PT range, and that includes at low PT. And that's one of the milestones that we were able to achieve in the last year. And these low PT tracks are important, especially in CMS, which relies on particle flow reconstruction. So you need to get even the low PT tracks reconstructed well if you can. One of the things we're currently working on is that, so this definition of efficiency only focuses on the long tracks. And we need to go back and make sure that we're still as efficient as CMS SW for shorter tracks as well. And we're working on double checking all of that and hope to wrap that up soon. Another new result from the group is our duplicate rate. So dealing with duplicates has to be done differently in our algorithm than CMS, because in CMS, when you build tracks sequentially, you can just skip seeds that have already been included in a track candidate. But if you're doing all of the seeds in parallel, then obviously you don't have that luxury. So we have a two-step process to minimize the duplicates. So first we try and clean seeds before we do any track building, but that can only remove so much. So then we also have a dedicated duplicate removal of track candidates after the track finding, and that's the new piece which is shown here. So we're able to get a duplicate rate less than 2% across the full range in Ada. This is with a very naive duplicate removal that hasn't been optimized yet. So we think we can do better, but we can show that we're already doing pretty well. I'm not showing fake rate plots today because a similar dedicated cleaning will be needed to get rid of the fakes in our algorithm, and that hasn't been implemented yet. So not showing those results today. Okay, so moving on to timing performance. So here I'm showing the speed up per event for the standalone configuration versus the number of threads. So on the left you have the Intel Xeon Skylake, and on the right the Intel Xeon Phi. And so the Skylake, the result on the left, is the target architecture for the CMS HLT. And so this is only for track building, so it doesn't include any of the overhead. But still, we see a pretty good scaling, especially at low number of threads. And this is true on both of these architectures. So, I mean, someone was probably going to point out that the Xeon Phis have been discontinued. Yes, we know, but the point is that we're not so tied to a specific architecture that we can still do well in both cases. We also can look at the speed up versus the size of the vector units. So because we're stuffing n matrices into our matriplex format, we can sort of artificially change how many matrices go in, or how many matrices fit in the vector register, and use that to look at our speed up as a function of the vector width. And so here you see that we can get a factor of 2.5 times speed up just from the vectorization. And so this is sort of for free, right? Because you're actually just using more of the same. It's not launching more threads or taking work away from anything else. It's just using the cores more effectively. And so if you use Amdahl's law, this tells you that 60 to 70% of our code is vectorized. And for a difficult problem like the Kalman-filter algorithm, that's a pretty high percentage of the code. But again, this is just for the track building only and doesn't include the overhead. If you do include all of the overhead, then you get speed ups versus the number of threads, like is on slide 23. So here, this is showing the speed up versus the number of threads for different numbers of events in flight. So the previous results only used one event at a time. If you increase the number of events at a time and get up to, say, 16, then you're keeping everything a lot busier, and you can get speed ups up to a factor of 25. And here, this is for the full loop, so including the I/O, the seed cleaning, and so on. All right, and finally, all of those results were with the standalone code. Obviously, we need to see how we actually do inside of CMS SW. And so that's what this plot is showing. So here, NKFit has only been used for the building. And so only the second column should really be affected by switching from CMS SW to NKFit. And this is a single thread test only using a TT-bar pilot 50 sample. And so you see that the average time to reconstruct or to do the track building for one event goes from over 500 milliseconds down to 120 milliseconds. So this is a speed up of a factor of 4.3 or so if you swap out the current CMS tracking with our tracking. However, we noticed when profiling, so I mentioned earlier that the data format conversions are painful and expensive. So that's what we see here. If we look at where the time is actually spent, we see that 40% of that 120 milliseconds is just doing the data format conversions. So going from MKFit to CMS SW and back. So if you ignore that data conversion time and just look at the time for the actual track finding, then we're a factor of 7 times faster. The core algorithm has been speeded up by a factor of 7. Another important thing to note from this plot is that track building, which has historically always been the thing that takes the longest in reconstruction, now takes less time than track fitting. So fitting one event takes about 220 seconds, and we are now underneath that. And we can potentially get even larger speedups if we use multiple threads, although that's obviously not a silver bullet, because then you're potentially taking work away from other things in the reconstruction. Okay, so this was my last plot. So just to summarize, the status of the parallelized common filter tracking, so MKFit, is well advanced. We have been able to show physics performance that's comparable to CMS SW across a wide range of PTs. On a single thread, if you use our algorithm, it's 7 times faster than the offline CMS SW reconstruction, ignoring data conversions, which is a big problem that we need to try and do better. The factor of 40% of time spent in data conversion was sort of our first attempt, so we think there's some low-hanging fruit to optimize that and do that better. Although more long-term, it'd be ideal to just settle on data structures where all of that reformatting isn't required. One of our milestones is that track building is now faster than the track fitting. Our next goals are to test the algorithm in the CMS high-level trigger environment, and we're working on that now and checking how our performance is if we use the online configuration. In the nearish future, we're hoping to publish a paper later this year documenting the algorithm and documenting this Matriplex library that we're working on. We also plan to do a production release of the Matriplex library so that it really can be used by the people outside of this first CMS application. And then, as I mentioned, we need to develop a GPU implementation of our algorithm, which we have several ideas for how to approach, but I didn't discuss much today. Right, that was all I had. Thanks.
Great, thank you. Questions?
I think you answered it already, but this Matriplex library is a standalone library, which I can just pick.
So we haven't done a production release of it yet, so it's not public yet. But that's our goal, is that we want it to be a standalone library, because that at least is very usable by others.
Okay. And MKFit itself would be is somehow tighter bundled to CMS-SW.
Right. I mean, it's still, in theory, it could be less so, because in theory, you just have to swap out the geometry. But there are more CMS-specific pieces that are wound up in MKFit. But the Matriplex code could be, yeah, that we do plan to release.
I noticed for the MKFit, you had one point you're talking about the parallelization of multiple levels, and you said that it was parallelizing on the regions in the detector, basically five regions in the detector. Is that something that would be adjustable, or is this really just intended for CMS-SW?
Yeah, so I mean, that's just how you divide things up. So yeah, that could be, I don't think it'd be that much work to divide it into other regions that make sense for different detectors, yeah, different geometries. It's just a way of another additional area of parallelization.
Anyone on video with questions?
Yeah, I had a quick one. I guess, have you only looked at this at pileup 70 TT bar? Is that, I mean, I was just wondering, your speedups and efficiency might be even better higher pileup. Have you looked at like pileup 200 or anything?
So pileup 70 is as far up as we've gone. One of the reasons for that is that we're still using, like, we haven't implemented the HLLHC, the geometry, like the phase 2 geometry of CMS. So I don't know if we'd necessarily get to.
Okay, right. This is your cylindrical cow, right?
Well, so we're at least doing phase 1 geometry now.
Okay.
We were doing an actual cylindrical cow for a while, but this is phase 1 geometry. But still, I think in order to get really sensible results, we'd want
the upgraded geometry.
The phase 2 geometry. Yeah.
Okay, thanks. Yeah, it just occurred maybe your results are even. I would expect them to even be differentially better when you're at high pileup, given what you
Right.
showed. But yeah.
Maybe I had a quick curiosity. So you talked about how you are not actually doing modules within MKFit. Do you think that's going to end up with any limitations for you in the long run? I mean, I know, for example, in Atlas tracking, we do use the module concept for some of the details. I was curious.
So right now, CMS is using all the modules. And so that's one of the reasons why we need to go back and use the current CMS implementation for the final fit, because in the final fit, you don't want to lose all that information about the geometry and the final modules. An additional area where we are seeing a little of an effect from that is that, as I showed on like the End Cap, like the actual CMS End Cap, you get a lot of overlapping modules. And right now, we only pick up one hit per layer. So if there are overlapping modules and there's a hit in both of those, as often happens, especially in like the forward pixel region, we only pick up one of those hits. So we do need to go back, and it's one of the things on our immediate to-do list, is to figure out some way to, probably in the backward propagation, to pick up additional hits from the overlap regions so that we really are finding all the same hits that CMS can find.
Okay, thanks.
Oh, sorry, Heather. I was wondering if you could talk a little bit more about the implementation of your simplified geometry for the end caps. Kind of how that actually plays out in practice, and what you feel the trade-offs are for that.
So I guess for the trade-offs, it's that we lose some of the precision and that we can't pick up all of the hits in overlapping regions because we're just trying to get one hit per layer. But really what we do is, we propagate the track to the center of the layer and then select the hit. And then if the hit is, obviously right on the center of the layer, then when we actually do the common update, we propagate the track to the actual hit location. But otherwise, this is all the information that we use. So I would say that overlapping regions are one of the main areas where we see sort of a drawback to this method.
But Lauren, this is Ravi. If I may, this was a choice up front that we made because it's not it's something that we woke up in the end and we say, oh my God, we do this. The plan was originally, because of the fact that there's a weak dependence on the radial position, and there's a conscious decision to try to gain on the thing that is the most expensive, which is the track building, by going to the simplified geometry, which has logical layers with semi-approximate radial dependence, precision on the location, and do the final fit in the context. If you want to go for the ultimate precision, you go and then load the full geometry. So it's a choice, basically, of what you want to battle. And in fact, I wanted to just add one last thing, is that if what we have never done is compare the precision of our fit to the CMS fit. And in the end of the day, you may even be in a situation that you ask yourself, am I so crunched for time that, as you see right now even, the final fit is more expensive than the track building, which is kind of amazing if you think about it. So we may even choose at some point, if resources push you to decide that you want to live with slightly less precision and reserve the very high precision to some extreme cases, like where you really care for it.
No, I think it certainly sounds like it's like a sensible choice, and something it's like it's also just a interesting. It's mostly just like a priori, I don't have a very good sense of really the impact of what that making that choice would have. So it's just interesting to see that in the end it doesn't really, I think you've shown it doesn't really end up affecting your the performance metrics that you've shown so far. So that's, yeah.
But again, to be precise, what we've shown you is not the question that Heather would ask. Who was asking earlier. It may have impact on momentum resolution, for example, and I expect it will.
Yeah, I would totally expect that.
Or impact parameter resolution or stuff like that. But yeah, so we'll see. But that has to be shown. If it matters and how it matters, you don't care about. Yeah, we'll see.
I had a question on I forgot what slide, it's the vectorization graph. I wanted to make sure I understood the units.
The Speedup one?
Yeah. This one. So where is ABX 512? Is that an 8 on this diagram?
I think that's 16.
Okay, so I didn't understand the units then. Okay. That's what I was trying to figure out. And then the overheads, see, you talked about this not including overheads, aside from the data copying, which I presume you'll find a way to get rid of. The overheads are a significant piece, or is really the overhead just the data copying?
So by far the biggest one is obviously the data format conversion, which we just basically need to talk more to the algorithms before and after us. There's one way to fix that.
Right.
I mean, there is other overhead like the I/O and stuff, which maybe you can get a sense for comparing 21 and 23, because here it's just the track building and the speed up for one event in flight, compared to here, where this has the full loop time, including I/O and the seed cleaning that we do.
Oh, okay, I'll study that. Thanks. Yep. Great. Anyone else with questions? Silence sounds like not. Okay, thanks everyone. I know this meeting happens, I think, twice next week. So where people come on Monday and Wednesday on different topics, we'll send announcements next week. So thanks everyone. Thanks Allison for presenting. Great.
Thanks. Bye.
Bye.